Had a set of 4 inequivalent consistent truncations of the sectors of the superstring. I'll remind you what they were. There was the guy we call type 2a, which went as follows. There was always the ns plus sector. But in addition, we had, in addition, we had the R plus NS plus. Then we had the NS plus R minus, I suppose, yes, R minus, and the R plus R minus sectors. This was type 2a. Then we had type 2b. NS plus, then R plus, yeah, something's wrong here. This is R plus NS. We want the left to be plus NS plus, yes. What?
Which one is right? And then this one just has plus, and the 2b has plus plus.
Yes, the R is a plus plus, exactly. Okay. And in addition, we have the sectors that we called 0a and 0b. The 0a sector was NS plus, and NS minus, Okay, and R plus, R minus, and R minus, R plus, right? Whereas the 0b was NS plus, NS minus, R plus, R minus. Okay, these were the consistent, these were the sectors that were all consistent. Just to remind you, what they obeyed was, they obeyed mutual locality, they were closure of the OP, and they allowed for non-trivial, none of these things were empty by level matching. And we put in some input about modular invariance to get this. Okay, now in in today's class, we're going to restudy the question of modular invariance. Okay, so
what was the check for chirality? One A's are non-chiral and B's are chiral.
B's are chiral, yes.
And what was the check again?
You see, because left and right, which one is which makes no difference. The question is there one plus and one minus, in which case it's non-chiral. Or if there are 2 pluses, then it's chiral. You know, as we will see maybe in more detail, but you see, for instance, in the R plus R minus sec, in something like R plus, you will get we will get the space-time spectrum will clearly not be invariant under interchange of plus and minus.
Yes, that sector will not be.
So this whole spectrum will not be invariant.
Yes.
On the other hand, this one will be.
What about NS plus R minus?
Which one? ns plus r plus and ns plus r minus, so these will get interchanged. You flip left and right, you get this, goes to that. Which one is left and which one is right makes no difference. You know, you get a, how do you get the spectrum?
Plus minus is not important.
No, no. Plus and minus is important. What? See, the chirality accounts only for Ramond sector.
Why do we have the 0 modes?
Where we have the 0 modes.
Okay.
Okay.
Only for the Ramond sector.
In the NS sector, plus and minus is very important, but it's not an issue of chirality, it's something else.
Yes, and that is because in our sector we have the 0 modes.
Because in the R sector we have.
Sector we don't.
Yeah. So in the R sector, plus or minus tells you whether you're keeping the anti-chiral part of the spin or the chiral part of the spin.
Yes.
Okay. So let's say, okay, let's actually see easiest here. You see, in this and this, we will get two sets of fermions, which are basically the same,
Yes.
both of which have the same chirality.
Yes. Yes. How did then we will get opposite, an R plus and R minus.
Exactly. Here you get an R plus and an R minus. So there's no chirality in the top spectrum, but there's chirality in the bottom one. Okay. Fine. So now let's see. In the last class, we had used some naive input from modular invariance. The first thing we're going to do in this class is to restudy the question of modular invariance. Okay. So, the first thing to note about these two spectra is that NS always just blank out the right moving side in your mind. Okay? Suppose you blank out the right moving side in your mind, you see that on the left moving side, whenever you have an NS, it's with a plus. And whenever you have an R, it's with a minus on the right moving side. Okay? Similarly, if you blank out the the right moving part in your mind, sorry, I blanked out the right moving part last time, so now you blank out the left moving part. Here, whenever you have an NS, once again it's with a plus. Okay, but whenever you have an R, I'm saying it the opposite, right? So I'm blanking on these guys, so it's also with a plus. So what we're seeing is that the projection we're doing, in this case, and you see the same is true here, in type 2A and type 2B, is a projection that is done separately for left movers and right movers. Is this clear? Okay? So if we write out the partition function for type 2A or type 2B theory, it will be the product of a left moving partition function times a right moving partition function. On the other hand, if you take the type 0A or 0B theory, you see NS plus appears here, but it's NS minus here. So it's not like NS is always in the plus sector.
But in type 2B,
yes,
you sort of do have that, right? Because the left is always going to be plus, or well, everything is plus.
Yes. So in type 2B, both the left and the right, NS and R are both always plus.
Yeah.
Okay. In type 2A, the left does one thing, the right does another. But what's important is that what the left is doing is not influenced by what right guy is paired up with.
So in general, in type 2 theories.
In type 2 theories, that's always the case. Is this clear? Okay. So what we have is the following. Okay. What we have is that what we have here is that, let's say for type 2A theory, let's write down the partition function. First, the partition function is going to be equal to product of two things, and I'll write out the product. The product on the left is NS, and we'll call it plus. Okay, whatever. Actually, let's break that whatever. How do we normally write it? It's Q to the pi L naught. Okay, plus trace in the Ramond times also plus q to the pi L naught multiplied by exactly trace in the ns sector with a plus, and now this q bar to the pi L naught bar and a plus trace in the Raman sector with a minus now q bar to the pi L naught bar. Right? This is a minus and that's a plus. And 2b would be the same as this, except that both would be plus. The left and the right parts would be completely the same. Okay? So if we study the modular transformation, in order to study the modular transformation properties of the partition function, in order to study the modular transformation properties of the partition function of the type 2A or type 2B theories, we can do that study case by case. Right? So we can first look at the modular transformation properties of the left moving part of the partition function, and then look at the modular transformation of the right moving, because it's product of partition functions. Right?
Generally, you are supposed to have an arbitrary linear combination of product each sector.
Exactly. What's special about this is that it's not a linear combination. It's just one term times another term. Yeah, you can always write it as product of terms sum. That's just Mira Suro.
That's generally.
Okay? But what's special here is that it's not sum over product of terms. It's just a product of terms. Okay? So let's look at each of these guys separately, and then we can put them together. Okay? This is something you cannot in general do. For instance, here, we have to look at them one by one. Okay? But for these cases, we can look at them separately. Right, like pure states and mixed states, exactly. Okay, so now let's see. There is okay. There is a part of the partition function that comes from the bosonic part of the theory. Okay. This is the x's and the bc's. Okay. Now the x's and the bc's give you modular invariant partition functions. Have we ever studied that in? Did we study that last semester? Can you remember? Did we talk about the partition function? Okay. So I'll give you 2 minutes about that. It's some very trivial thing, but the point of that is that, let's say each x, the partition function for each of the x's is by itself modular invariant. So let's do a small aside. The main point of today's lecture is the fermions, which give all the fun, but we've not studied the bosons first. We should quickly do that. Right? Including the central term. The central term will be needed for the modular invariance. Right. What?
It's not Liouville action. It's modular invariance.
Just modular on a torus.
Yeah, this is a reasonable theory. Therefore, its partition function when you take holomorphic and anti-holomorphic into account, it will be by itself.
Just by itself, modular invariant. Exactly right. Exactly right. It will not have this. By the way, yeah. Let's work it out. Sorry. I should say that this product structure is in spin structures. So the part that will truly be a product will be the fermion part. Okay. So let me say it again. This whole thing here will be a partition function. This is true. What I've said is true. But it's not true that each of these by itself Okay, in the bosonic sector, this is a bit imprecise because there are modes that you see in the bosonic sector the zero mode is neither left moving nor right moving. So to say trace in the left moving sector and trace in the right moving sector is a slightly imprecise thing to do for bosons, because there's the zero mode which is neither in the left moving sector nor in the right moving sector. It's just there. Okay, so what I've really done here, this thing should be thought of as the fermionic part of the partition function. Okay, so the whole partition function has a bosonic part and a fermionic part. As we will see, the bosonic part plays essentially no important role in the discussion for modular invariance.
Because the boundary condition for boson is periodic. Yeah.
Because say that again.
For boson,
it's
in the time direction it's periodic.
Uh-huh.
And in the space direction also it is periodic.
Because the boundary condition for yeah.
Because this is goes into itself under modular transformation.
This is part of it. But you see, this stuff also naively goes into itself under modular transformations. As I will show you, this part by itself is naively modular invariant. This part by itself is naively modular invariant. But it will not, I mean, there will be slightly more. Okay, so let's look at the bosons for a minute. And then we'll come back to the fermions, which is really the interest of today's lecture. Okay, so suppose I want to compute trace q to the power L0, q bar to the power L0 bar for the bosons. Let's first do it for the X field. Okay, so let's say we've got one X field. Then we'll do it for all 10. Okay. So we've got one X field, we'll soon do it for all 10. Well, this is very easy, right? Firstly, there is a ground state energy. That ground state energy is now, was it L0 is minus 1 by 12 or minus 1 by 24? 1 by 24 because the Hamiltonian was L0 plus L0 bar. Right. Okay, excellent. So first, because the ground state energy is minus 1 by 24, we'll have q to the power minus 1 by 24. On top of that, we'll build up the whole spectrum. Okay? Then we'll have the integral over the zero modes. We'll discuss that. Zero mode. And then we have all the oscillators. Now the oscillators are easy because the oscillators have energy 1, 2, 3 up to infinity. The oscillators are bosons. So we have product n is equal to 1 to infinity. 1 over 1 minus q to the power n. And just for fun, I'm combining together so I don't have to write two product signs, I'm combining together the holomorphic and the anti-holomorphic oscillators. Is this clear? This is the partition function. Now, of course, to make this a real formula, I have to replace this bracket zero mode by something.
So there would be a q bar to minus 1.
Thank you. That's q bar. Thank you. Okay?
P of this bosonic sector goes into itself. They are mutually local.
Yes.
And their boundary condition is also invariant under modular transformation. These three facts together is it not going to
guarantee that this is modular invariant?
Local
Yes, so there's one more thing. The thing is that the bosons have are being studied in a way that allows regulation of the path integral. Okay? You can take, if there's any divergence, you can take a mass term, for instance, okay, and regulate that divergence. Here, because we're going to do different things on the left and the right, that makes many formal statements simply formal. Because they're statements about integrals that give you infinity and may not be regulatable in the right way. So, but you see, the bosonic theory, what we're doing is just completely right. On the other hand, in the bosonic theory, were we to separate the left moving part and the right moving part of the zero modes, and treat those somehow independently, or do something that is not taking the boson and putting it on a, putting it on a circle, then we would run into trouble. Because that's the kind of thing that you shouldn't do. If you have a nice local Lagrangian which you can regulate all divergences from, everything's going to work. But you take things inspired by that local Lagrangian, then you start separating things out, then you might get into trouble. Okay? That's the analog of treating left and right movers separately here. Okay? But of course here we've not done any of that. So you're right, we've got a Lagrangian. We've studied since we entered PhD how to regulate bosonic Lagrangians. It's all good. So it's guaranteed to work. But I just want to show you in formulas how it's going to work, because we'll contrast that with the fermionic formulas, which there will be subtleties. Okay, so now let's look at this zero mode part. What was the zero mode part? Well, we had this Lagrangian, which was 1 over 4 pi alpha prime, and then integral del mu x, del alpha x mu, del alpha x mu. But for the zero mode part, we do the integral. That gives us an extra 2 pi, so that's 1 over 2 alpha prime. And then that's just x0 dot square. So what's left is the partition function. What's left is q what's left is the partition function of this Lagrangian. Okay. Now let's see. First, suppose I had this Lagrangian. This is just non-relativistic quantum mechanics of a particle with mass 1 by alpha prime. So we know its spectrum. Okay. So we know its spectrum. The spectrum is trace e to the power minus beta h.
Where are we? Is this on the torus still?
This is, you see, we're computing a torus partition function,
Yeah.
but we're going to compute the torus partition function by thinking of it as trace over a Hilbert space.
Okay. No, I mean, is this spectrum going to be discrete or continuous?
It will be continuous. The target space is continuous. Yes. So it's just the free boson. This X had no periodicity. Okay. So we've got trace e to the power minus beta h. Now h was what? H is just a Hamiltonian. We have to write that, remember, in terms of P and Q. Yes. Exactly. Trace of e to the power P squared over 2m, which was alpha prime by 2, because m is 1 by alpha prime. Okay. Trace is what? Well, we all know this, right? This is dp by 2 pi times the factor of space-time volume. Okay. And so now if we did this integral, we could actually do it honestly. And then we want to minus, because this minus beta. Okay. We could actually do this honestly, keeping all the factors of 2 and pi and so on. I'm not going to bother. We can actually do it and do it very precisely. But this will, the important thing is that it will have a factor of 1 by square root of beta. Then there'll be a volume, there'll be some pi's, there'll be some alpha primes, there'll be 1 by alpha prime if we want to keep that. There'll be some pi's and there'll be a volume. But the really important thing is this 1 by square root of beta. Okay. Now, what we had was q to the pi L naught, q bar to the pi L naught bar. Okay. If we wrote q as e to the q is equal to e to the power 2 pi I tau, which is standard notation, then that becomes e to the power 2 pi I tau into L naught times e to the power 2 pi I tau bar to L naught bar with a minus. Okay. Now L naught plus L naught bar therefore couples to tau plus tau bar, tau minus tau bar. So we can write this in terms of sum and difference of L naughts, L naught with L naught bar. L naught plus L naught bar is what we call the Hamiltonian here. Okay, so you see that the role of beta is played by the imaginary part of tau. Is this clear? In fact, more precisely, more precisely, we can just get this by setting L naught equals h by 2 and L naught bar equals h by 2. And so we will get pi times 2 pi times 2 pi times in tau is equal to beta. What? L naught plus L naught bar. And these states have L naught equals L naught bar. Okay, so we can just set L naught and L naught bar equals h by 2. Okay, so this will become 2 pi I times im tau times, the 2's cancel because when you take the difference you get twice the imaginary part of tau. Okay, so if we were keeping factors of 2 pi, which Polchinski who does religiously, okay, we would have to worry about this 2 pi, but at our level of precision, okay, this 1 over square root of beta just becomes 1 over square root of im tau, which you can then write in terms of q and q bar if you wanted to, but it's nicer just to write it as im tau. Okay, and so the purpose of this jugglery here was to get a precise line here, this q bar to the power minus 1 by 24 divided by square root of im tau times this product 1 minus q to the power n 1 minus q bar to the power n. Okay, now this quantity is a famously modular invariant thing. Okay, this can be written in terms of what are called eta functions. Okay, eta functions are defined by these products. So let's say eta of q is defined by, I'll write it down once. Not that I will try my best not to use this terminology, firstly because I'm shaky on it, and secondly because, okay, who cares? But this one is simple enough that even I remember it. It's eta of q is equal to q to the power minus 1 by 24, product n is equal to 1 to infinity, 1 over 1 minus q to the power n. Okay? And mathematicians, I don't know, 100, 150 years ago, whenever they were doing this, defined this quantity, and you might think it's sort of curious that they defined it exactly as we wanted, including the q to the power minus 1 by 24. What were they doing? Why is it exactly what we want? And of course, the reason they did it was they were interested in properties that had functions that had good modular transformation properties. And in fact, they defined this with the observation that this, if you divide by 1 over square root of im tau, is a modular invariant function. That this has the modular transformation property that is exactly cancelled by the modular transformations of 1 over square root of im tau. Yeah, the 1 over 24 is totally crucial. So this 1 over 24 that we got from 1 plus 2 plus 3 is equal to minus 1 by 12. It was totally crucial to maintaining modular invariance, because it was important to maintain conformal invariance, if you remember. Yeah, so mathematicians from their own point of view had already defined these functions, had already studied them, which is of great help to string theorists. Okay, so this is a nice modular invariant partition function, and that's great. That's all I wanted to say for the on the bosonic side to start with. Sorry, for the x's. Let's also though worry about the BC conformal field. Okay, so what have we got so far? What we've got so far is that Z of 10 free bosons Okay, actually let's first work it out in the bosonic case, just to see everything's working out really nicely. So Z of 26 free bosons is equal to q bar to the power minus 1 by 24 product n is equal to 1 to infinity 1 over 1 minus q to the power n 1 over 1 minus q bar to the power n im tau square root the whole to the power 26. I want to show you that something nice is going to happen in the bosonic string. Okay, and then we'll come and see the same nice thing in the fermionic string. But because the central charge will only vanish with BC, with the BC system and just the bosons in 26 dimensions, this nice thing that will happen with just the bosons will happen in the bosonic string, as you'll say. Okay, this is good. Now let's look at the BC conformal field theory. Okay, so now we have to work a little bit. Firstly, there's q bar to the power what? That's the first question. You know, what's the 0 point energy? Okay. Exactly, exactly. You remember the ground state of the bosonic of the BCCFT was the operator C, which started with scaling dimension -1. Okay. Then the BCCFT had central charge equals -26. So the general formula for the transformation from plane to cylinder gives you an energy which is minus C by 24. So if the energy on the cylinder is more than the energy on the plane by minus C by 24. That's why in the case of the boson, when the vacuum energy was 0 on the plane, it was minus 1 by 24. Okay? So here we are going to get more by minus C by 24, but C is minus 26. So more by 26 by 24. Okay? But less by 1 because the energy of the ground state was 1. Okay? So we will get minus 2 divided by 24. Plus 2 divided by 24. Because 26 by 24 with a plus, minus 1. Is this clear? Is this clear? This was plus 26 by 24. That was the map from plane to cylinder. Minus 1, which was the ground state on the plane.
Basically, you are saying that you should not care about this C by 24 when you combine bosons and C.
Exactly, because C cancels out.
The combined system has central charge 0, so we can just forget the central charge and get the energy for the ground state.
Exactly. 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 Exactly right. Okay, and now let us look. Now let us look at the. Partition function for the BC system. Now, the first thing about the BC system, okay, is that B and C. Firstly, what was the spectrum of oscillations for the BC system? What were the energies of B or C? Oscillator energies. Come on, you guys remember this. It was 0, 1, 2, 3, 4, right? This is B0, B1, B2, B3. Right? Okay. The 0 modes gave us some ground state degeneracy. So we'll get some number. We'll actually get a factor of 4 because of the ground state degeneracy. Okay. Let's forget about that. We're not keeping such precise things. What we care about are the non-zero modes. And they have energies 1, 2, 3, 4, 5. Now we have two questions. A, when we compute the partition function over the BCCFT, what boundary conditions do we use in the time circle? But there are no options. We have to do the same that we do for every bosonic field. Because BCCF, for instance, C came from diffeomorphisms, which were periodic around time cycle. So when we compute the partition function over the BCCFT, we have to compute it using periodic boundary conditions for B and C over the time cycle. What is the Hilbert space interpretation of that, given that B, C are anti-commuting fields?
Just by the fact that they're anti-commuting, doesn't that mean that they have to be anti-periodic?
If you were computing trace over the Hilbert space, they would be anti-periodic. But that may not be what we want to compute.
I mean, the argument for why things that anti-commute have to be anti-periodic in a compactified time, that's just manipulation. It's not like any...
It's manipulation for computing a path integral representation of a trace. If you want to compute something else, you might get a different boundary condition. You know, there's a path integral. As a path integral, I can compute whatever I want. Now, you see, our job is exactly the reverse of your question. Our job is, we know from physical considerations what a boundary condition is, and we have to translate that into what trace over a Hilbert space we're computing. But how do I go change boundary conditions? By inserting -1 to the f. So clearly, the path integral we want to compute is not trace over the BCCFT, but trace with a factor of -1 to the f. That's what is relevant for string theory. Also remember that BCs are fermions. So each oscillator is excited 1 time or 0 times. So now I'm going to write down the partition function and you tell me if you believe me. This is product n is equal to 1 to infinity, 1 minus q to the power n in the numerator. Exactly. So this is trace of -1 to the power f. -1 to the power f of this BC system.
What did you write for there? You took into account that other thing that
The ground state degeneracy.
the thing that is thrown out?
Yes, I took into account the thing I've thrown out, and then we can argue about whether we should take that into account or not. Let me just say number. The B0 equals 0, that physical state condition. This is some number here which we could argue about. At the moment, let's not worry about that.
Yes, but what should you do? You should throw it out?
Let's see. Let's see. Should we throw it out or not? Probably not. Probably not. From this point of view, should we count that as 4 or 2? I think probably not. Let me see what Pulchinski does. A lot of this anyway will get absorbed, the overall normalization of the path integral will get absorbed into what your string coupling is and so on. It would make very little difference. But there is a logical answer to your question.
It can't affect modular invariance.
It won't affect modular. But he wants, anyway, just in principle, should you keep it or not? Wait, let me see what he does. Where does he do it firstly? One. I know what. The thing that will throw it out is the insertions. That will not be the fault of our interest, because we have the insertions of the B and the C. I mean, at least in any S matrix kind of thing,
Yes.
we will have some, let's say we were on the sphere, or let's say we were on the torus. We will have an insertion of a B and a C, because there are zero modes.
Yes.
And those will project onto, we'll only take the C0 and B0.
Yes.
And those will project onto particular vacua, which will be exactly what we want.
So then you will not take.
We will not take that into account. We will not. When we write down the actual formula we want to evaluate for anything physical, it will become very clear. It will just the zero modes of B and C that will actually project onto the one that we actually count physically also. Yeah. Okay. So sorry. So ignore this. I think for what we actually want, we will just ignore it. Okay. But let me see if this guy does something. Just a minute.
When we have various non-trivial background, like we have things like linear combination, like theta angle. And for example, if you don't take that, some cluster decomposition doesn't work. In Gauss theory, in Young-Mills theories.
Yes. Sorry. I was spacing out. Sorry. Yeah.
When you
Yeah,
have
please.
non-trivial ground state.
I just let me check whether he. Yeah, he does not have the 4. Yeah. Okay. Yeah.
When one does this non-abelian, this Young-Mills theories, and when you have non-trivial vacuum,
Yes.
then you put a theta term,
Yes.
taking into account contribution from various ground states.
Right.
Here nothing like that, and if you don't put that, probably something goes wrong.
Yeah.
That cluster decomposition goes wrong. At least some people.
Yeah. Right. Well, of course, theta could be 0. Right. Yeah. But here, let me just continue on what I was saying. You see, had I been computing, I did something actually even conceptually wrong. I wrote that 4, pretending I was computing trace over the Hilbert space. That would have given me 4. But you remember the path integral we computed was not trace over the Hilbert space. It was trace with a -1 to the f. Now if we do the integral over the 0, if we compute the trace over the 0 mode sector with a -1 to the f, we'll get 0 times 0. Because on the left we have 2 states which differ by fermion number. One fermion number, so we'll get 0. And on the right we have 2 states which differ by fermion number. This is of course the familiar fact that if you have a fermionic path integral and there's a fermionic 0 mode, the result of that path integral is 0.
Could you explain that logic again?
If you have a fermionic path integral and a fermionic 0 mode, the result of that path integral is 0. This is this fact. Integral d theta, where this is an anti-commuting number, of 1 is equal to 0. So C0 and B0 doesn't enter into the action, but it enters in the path integral measure. So it will just give you 0. So the quantity that I wanted to compute would just have been 0. But if that's not the quantity you really want to compute in string theory, because there are the 0 mode insertions. Okay? So with the 0 mode insertions, now that's not 0. That's what the 0 mode insertions were for, right?
Yes.
And that projects it to a single, to a unique ground state. Okay. So sorry. Yeah, so that 4 was stupid. 4 should never have been there. I mean, by no stretch of logic should it have been there. It would have been there had we been computing trace e to the power minus beta h, but we're not. Okay, great. Okay, but the important thing to remember, to note here, is that at least in the oscillator part, this gives us exactly the same thing we had in the denominator for the bosons, but now in the numerator. Okay? So let me multiply these two things together and see what I get. Okay, so what do I get? What I get is product n is equal to 1 to infinity, 1 over 1 minus q to the power n, 1 over 1 minus q bar to the power n, to the power 20 form. Then what remains is now what? We get this whole thing was q bar to the power minus 26 by 24.
1 by q.
We get 1 by q bar, exactly right. Q bar to the power minus 1.
Minus 1 was dimension of
Which was the ground state energy of the full theory because C was equal to 0. Okay. Okay. And you get im tau to the power 26 by 24. Is the square root was what to be?
So then, it's just then and not. Why do you have 1 by 24?
I'm sorry. Right. Thank you. Im tau to the power square root 1 over square root im tau to the power 26.
There is just one factor, two factors in the 1 minus q to the power n in the numerator.
There is just sorry. This was square and square. Thank you, because each of B and C had their own oscillators. Thank you. And because of that square and square, we have actually the 24. Okay. Now what's going on? What's going on is you see, this looks very good except that this was 26. This we'll write as 24 times 1 by im tau. Because as Yankee observed, it was just, what that was 13. So we made it 12 and then 14. Now, this is precisely the combination needed to make the whole thing modular invariant. This is like 24 free bosons. But there's still this 1 by im tau. And you know that extra 1 by im tau is actually needed in string theory. Because as we will see, I will show you as we go along, what we're going to do with this, it's an integral which is like d2 by, over the modulus of compactification of the torus. Right? d2 by im tau. And in fact, this here is the SL2R invariant measure. Okay? So the thing that we wanted wasn't something completely modular invariant. We wanted the thing that which would combine with d2 to give you exactly this measure.
So in other words, if we consider somehow tau to be like another free parameter, and then in doing our partition function, we would integrate over all powers of tau, this is what we want to look at the end.
Yeah, if you want a modular invariant, you know.
This is sort of like the tau that's
SL2R, SL2Z invariant
yeah,
measure.
yeah, modded out by all the...
Exactly, exactly.
Yeah.
This is basically exact as you say. We will see when we actually use this formula in detail how these things come about, their modular transformation property. But now it's plausible enough, right? You've seen this formula many times. d2 tau by im tau is the right measure. Okay, so this is exactly what we wanted, and is exactly what we're getting. Okay, now the question is, how does the same thing work? How does the same thing work for the fermions? Okay, so you see, by the way, there's a lesson here. What did the ghosts do to the free x's? It ate up 2 of the free x's, and then left as much im tau as was needed to make the measure happy. Okay?
For fermions also you have a modular? Or not?
What? Yes.
Then you will also get a tau.
You're asking, is there an analog of tau, like a fermionic analog of tau? Yeah.
Tau is describing your manifold. It's not a field on your manifold.
It was telling me equivalent matrices.
Inequivalent metrics, different metrics that cannot be reached by Weil transformations, conformally inequivalent metrics. No, so no, but why not? Let me think just.
The metric itself is going to be a field on your worldsheet. Tau is not a field on your worldsheet. It's describing your worldsheet. It's describing the inequivalent worldsheet on which you can then put on a metric and have it superpartner. But tau is not a field that's going to have like a super direction associated to it. It's like the genus, right? It's not.
It's parametrizing the conformally inequivalent metrics
Right.
you can put on a genus G manifold.
No, but I'm saying, thinking of tau should be thought of like the same as you think of a genus. Right? You don't have a superpartner to the genus.
I'm saying that there was a spin
Mm.
to current,
Yeah.
which was fermionic current, and that current came from sort of gauge fixing some fermionic gauge invariance. There, when you gauge fix it, you still have this inequivalent structures.
Yeah.
Equivalent.
Yeah. Give me a minute. So. This is in a way the question of the number of zero modes of the beta gamma system, right?
Yes. Number of derivative tau insertion was
Yeah. Yeah, the number of zero modes of beta and of gamma, and surely beta and gamma, I mean, will have, but maybe the fact that it's half integer dimension makes it not have. Let's check. Okay.
But beta gamma system was related to fermions, and you said you will put different boundary condition for fermions. So that half will never get compensated for some boundary condition.
Yeah, it's a good question. Let's just check though on the sphere whether there are no boundary conditions. Let's check on the sphere whether there are no boundary conditions, how many zero modes beta and gamma have.
Are you having this half now, or?
Yeah, I think that the half will kill it.
Yeah, so if unless this half gets compensated by a boundary condition, you will not have anything.
Yeah, you will not have anything.
If half gets compensated, then you might have.
No, it sounds right what you're saying. It's true that in the Ramon sector, for instance, the beta gamma system had zero modes on the cylinder, and we sort of artificially projected them out, right? Maybe this picture business is effectively dealing with the zero modes. It's a good question. Give me a minute. For instance, if you say you take a torus and you take periodic boundary conditions on conditions such that this is beta gamma periodic on both, they certainly have 0 modes.
Sometimes you said infinite number of them, I don't know.
No, the number of states that you get by quantizing the 0 modes is infinite.
Yeah, that's that ground state, that was infinite.
Right. The number of 0 modes will be finite.
This ground state will be a representation of that algebra.
Right. And yeah. So, right. Now, this is going to be dealt with in the following way. You know, sort of like the B and C insertions projected onto particular states in this. The B and C insertions dealt with the 0 mode part. The insertions of that we will put with the superconformal coast will make the path integral finite, and so basically effectively deal with the 0 modes, because these are the things that would otherwise have given either 0 or infinity depending on how you count in the beta gamma system. So they do have 0 modes and they're going to be dealt with, but it's not like we're supposed to.
But here, because you had 0 modes, the number of detailed directions are related to B0 modes, I guess.
Yes, was beta. Yes, was B0 modes. Correct.
B0 modes. So once you have beta or gamma, one of them, right? The one that is analog of
Beta.
Yeah. That
Yeah.
sorry, that has 0 modes. Then you will have the directions.
Yeah, but you know, you have these directions, but the integral, see, there's no finite version of a fermionic 0 mode. Right? It's like you take a bosonic 0 mode, and then that's a small thing and becomes something finite. That's this tau. For the fermions, you have no more than just the integral over the 0 mode. The integral over the 0 mode itself will be sort of like the integral over this tau. Okay. But the final formula is not going to have any analog of. There's not going to be some finite fermionic finite integral of that sort. It would have to be some finite fermionic integral, right? It's not going to have anything of that sort, but it's a good question. Okay, let me think about it and get back. Let's say on a torus, for instance, we should be able to work it out by gauge fixing the supergravity thing and so on. It's a good question. I don't have a clear answer at the moment. Yeah, but the final formula will not have that. Sorry, people. Sorry, I'll just get back 1 sec. As you can see, I'm pretty incompetent in using this phone. Hi, people. Okay, yeah, sure. I'm in the middle of class now. So, yeah, I'll come. Yeah, we can go after I come. Okay, yeah. Okay, sorry about that. So, let's move on. Okay, so once again now, what we're going to want to do is to look at the partition function of the fermionic sector. Now, just like for the bosons, the effect of the BC system, in the end, is going to be to kill 2 of the fermions. Okay? So I'm going to first assume that that's how it works, work basically in light cone gauge. Okay? And then we'll come back and see how that works in more detail. Okay? So now we're going to try to compute trace Good. So with all of that, now so let's hurry now. So now we're going to try to compute the trace in the NS sector, and we're going to need this in, let's say, plus or minus, because we're going to need it for for both type 0 and type 2, and we're going to q to the pi L0, and we're also going to compute trace in the Ramond sector for both plus and minus of q to the pi L0. We're going to compute this. Now, in the NS sector, okay, let's, yeah. It's probably useful to do a more general calculation. So let me tell you about the more general calculation we're going to do. Okay. So consider the quantity which is Z alpha beta. Polchinski defines this quantity Z alpha beta. Z alpha beta, which is trace in the sector labeled by alpha boundary conditions on space and beta boundary conditions in time. Trace of q to the power h times e to the power I pi beta times q. Okay, so let me explain what this quantity is and why we're interested in it. Firstly, what I've done is taken fermions and pair them up in pairs. Okay, so I've taken the fermions and paired them up in pairs, and one of the so I've taken, let's say, psi 1 plus I psi 2 and psi 1 minus I psi 2, like psi and psi bar, like we did in our discussion of bosonization. Q is the operator that gives psi charge 1 and psi bar charge minus 1. Okay, so what we've done is to take psi 1 plus I psi 2 is equal to psi, and psi 1 minus I psi 2 is equal to psi. Now, we're always on the left moving side, okay? When I say psi bar, it's like in the discussion of bosonization. Psi bar is psi 1 minus I psi 2. There's no right mover in sight. Is this clear? Okay, and Q is the operator such that it assigns charge 1 to psi and charge minus 1 to psi bar. It's the operator which under bosonization will translate into the translation current. Translation of H. It's the operator whose current will be psi bar in fermionic language or del H in bosonic language. Okay?
One of them is e to the phi, one of them is minus phi.
What?
One of them is e to the phi, one of them is e to the minus phi.
One of these things is, this thing is e to the power IH, and this is e to the power minus H.
And then if you shift H,
then if
one of them gets
shifted by plus and the other one by minus. Exactly. Now, why are we interested in this strange object? Notice that
beta equal to 1 will translate into putting minus onto the current.
Exactly. So Indranil's got it. Suppose we put beta equals 0, then we're computing just the simple trace over the Hilbert space. Now computing simple trace is same as putting minus 1 boundary condition, anti-periodic boundary conditions on the time circle. Okay? So beta equals 0 is anti-periodic boundary conditions. Okay? On the other hand, beta is equal to 1 is trace with q to the pi L0 times minus 1 to the pi f left. Okay? And this is trace with periodic boundary conditions. Okay? Now, when we project onto the sector with, when we had our NS plus, for instance, Okay, so what was trace
Beta was 0 for
ns
NS.
plus? What?
Yesterday we had beta was 0 for NS sector and 1 for Raman sector.
Yeah, it's the same beta. Or is it flipped? Anyway, we'll see. Yeah, beta was
Space part. That was for space part.
yeah. Let's see. So trace of yeah. That was for space, I think. Yeah,
This is time.
this is time, right? So trace plus is what? This is half of trace in the NS sector into 1 plus minus 1 to the power f. Because you're projecting onto fermion number is equal to plus 1 times, of course, always q to the power 0. Okay, so this will be equal to half of, now the first guy is the simple trace. So this will be z 0. Okay, now I have to tell you about this beta. Sorry, before I translate that, I have to tell you about this beta. Beta is simply what your boundary conditions are.
In a sector, ground state has fermion number 1, right?
NS sector ground state has fermion number. Oh yeah, good point. Am I accounting for that or not? You're absolutely correct. You're absolutely correct. So if I don't take into account the ghosts, if I do it in this light cone way, then this should be trace of 1 plus minus 1 to the power f left. Right, because the ground state has, is because of the ghost part. The ghost part has a minus 1 and then the fermion number builds on that. Thank you. Absolutely right. Okay. Okay, good. So, and what is this beta here? This beta here is the beta here is the boundary condition as you go around. So the boundary condition we're looking at is psi of sigma plus 2 pi is equal to e to the power I beta into pi. I beta into pi times psi of sigma.
Your alpha is the space part, right?
No. Oh, right. Sorry. Alpha. Thank you. Beta was in time here. Yes. Thank you. Maybe I should have. Anyway. E to the power I alpha pi times psi of sigma, and psi bar of sigma plus 2 pi is equal to e to the power minus I alpha pi psi bar of sigma. Okay. So in the NS sector, we are anti-periodic on the circle. Okay. So in the NS sector, we are anti-periodic on the circle. So saying that we're in the NS sector is the same thing as saying alpha is equal to 1. So now let's translate this into a formula. So this is half of Z10 minus now this guy was 1, right, because of the minus 1 to the other. This is the minus Z11. And have I got the space and time part right? I've flipped that, right? I'm sorry. This is always, NS is always 1. So 1 I had for space, right? And here I had for time, so this was 0, 1. Yes. Okay. So, And you see that if I wanted something in the Ramon sector and the minus, I would easily be able to translate into this language. There'll be bunches of z's with zeros and ones in different places. We just have to keep our wits about us for what is which is space and which is time, and we'll get it right. Okay? So clearly, if we know how these z alpha betas transform under modular transformations, then by putting things together, we'll get everything. Okay? So the task we set ourselves is to try to understand how does this z alpha beta transform under modular transformation. So first, what we'll do is compute z alpha beta, and then try to see how it transforms under modular transformation. Okay. So the computation is, of course, quite easy. What we're doing is computing a trace. Because we're computing a trace, we're just computing the trace. So we're going to do this calculation just by going to Hilbert space. So we've got oscillators of we've got the alpha oscillator, the psi oscillators, and the psi bar oscillators. Okay. Now we have to remember what the moding of the psi, moding of the psi oscillators and the psi bar oscillators was. Okay. But remember what we had was that psi of sigma plus 2 pi was equal to psi of sigma times e to the power I alpha pi. I'll just check if Pulchinski is alpha or minus alpha.
The Raman sector is okay, so e to the minus pi alpha
Where is this definition? Just
alpha square by 2 is the dimension for ground.
Yeah, I think it's just I alpha pi. And psi bar of sigma plus 2 pi is equal to psi bar sigma e to the power minus I alpha pi. So now let's do the expansion of this guy. Okay.
You want the bosonized ground state for this boundary condition, right?
Well, no, I want just the oscillator. I want just the oscillator spectrum. There are two things. There's the ground state energy and the oscillator spectrum.
Yes, so ground state will be e to the I alpha h.
Ground state, correct, will be e to the power I alpha h. That's correct.
The dimension is alpha square by 2. This is from 0 to
This will alpha squared by 2. Exactly right. Exactly right. Exactly right. This is for the vacuum, and then we will have whatever shift we have from going from the cylinder, sorry, from the plane to the cylinder, which in this case will be 2 by 24, minus 2 by 24.
2 because
No, minus 1 by 24, because it's psi and psi bar, and that gives c equals 1.
yes, psi and psi bar gives you 1.
Right.
Yes, and then 1 by 20.
Minus 1 by
1 by
20.
24.
Exactly. So we'll have that. But before that, I wanted to just get the oscillator spectrum. Okay. So what's the moding of this guy? The moding is
You want to see the cylinder?
what? Yes, on the cylinder. So psi is equal to, well, it doesn't matter, but okay. Suppose we were on the cylinder. Psi is equal to sum over n e to the power I n sigma, where n belongs to what? N is equal to, n belongs to z plus alpha by t, alpha by t. Right, because 2 pi I as you go around. Right, alpha equals 1 will make it half integers.
Alpha equal to 0 is the Raman sector.
Alpha equals 0 is the Ramond sector. That's right. Alpha equals 0 is the Ramond sector because it's
That should be integers, and alpha equal to
1,
should be half integers.
which it is. Okay. And so, on the other hand, what is the what is the moding for psi bar? The moding for psi bar is similar. This is for psi, but n goes to z minus alpha by 2 for psi bar. Okay, so now let's compute this z alpha beta. Let's keep this line here. And
considering more options than alpha equals 0 or 1?
what?
Are we considering other options besides alpha?
We're never going to consider, for this problem, we're never going to consider it. Later in Polchinski, he sometimes considers orbifolds, for which this more general formula is useful. That's why he's working it out here. And because it's as easy to work it out for general alpha and beta. Okay? In fact, in some sense, it's easier because you work it out once and for all. You don't write many cases. But for our current purposes, alpha is always 0 or 1. So if it helps you, just think of alpha as 0 and 1. Okay. So now it's straightforward. What do we have? We've got firstly the oscillator part.
You will do infinite sum to get the answer, looks like.
What?
This is why you wanted the moding.
Infinite product.
You want to calculate the ground state energy.
No. I just want the whole partition function. So the partition function itself comes from exciting the various oscillators. The oscillator energies. So that infinite sum is accounted for by your alpha square by 2.
Yes, minus c by 24.
Minus c by 24. So we don't need to do that again.
Yes, you could have get that from infinite sum.
We
I thought
could.
You might have done that.
Yeah, you could get. In fact, we have done something like this at some point, right? Yeah. But we're not going to spend the time on that at the moment. Okay. So let's see. So for let's suppose that alpha is always a positive number between 0 and 1. Okay? Things get funny if you go around. So there's spectral flow. But forget all that. Suppose alpha is a positive number between 0 and 1. Then we want to get, the oscillators are things with negative. Okay? So we will get the contribution from n is equal to minus 1. I mean, this is integer is equal to minus 1, minus 2, minus 3 here. Okay? So we'll get product n is equal to 1 to infinity. And then we will get what? 1, no state. And now the next guy will be what? It will be plus we've got this factor of trace e to the power I beta q. Our psi carries q equals 1. So e to the power I beta times pi, okay, times the energy times q to the power 1 minus alpha by 2. N minus alpha by 2. N minus alpha by 2, n is equal to 1 to infinity. And then I have to dress with this. First, let me write on the oscillator part, then I'll write on the overall outside. What? Exactly. Then let's look at the other. Let's look at the other guy. This guy will start with 0.
Why is the e to the I beta pi not in the first term as well?
It's not on the first term because you see each psi photon has charge 1. So the psi vacuum is charge 0. So this is the charge of the psi photon. And this is the energy of that psi photon in the nth oscillator state. And then we will have here n is equal to, I'll put an e to the power I, okay, let's just write it separately. Product n is equal to 0 to infinity, 1 plus e to the power minus I beta pi, q to the power n plus alpha by 2. Okay, and now we're running into some conflict because Polchinski has his alphas replaced by 1 minus alpha. I just have to figure out what his alpha definition was. Oh, I'm really sorry. Polchinski is working with psi of sigma plus 2 pi is equal to, I'm really sorry, it's e to the power I pi into 1 minus alpha. Sorry, people. Every time we had an alpha, we're going to switch to 1 minus alpha. So all this was, in our old conventions, alpha went down, right? No, alpha went up. So these would all be zeros. Okay? And everything here would have a 1 minus alpha. Okay, now do I get Polchinski's oscillator part? Right.
You wrote the level of n by looking at when the positive energy starts, right?
Mm-hmm.
One of them it starts at 1.
Yes. And then what he does is to shift this n thing in one of them. Yeah, so in here, we'll make this also n is equal to 1 to infinity and put a plus 1 minus 1 here. So this becomes like alpha minus 1. So let's stick to what we had. And then he writes this as, I'll just write it down and then we'll see. Minus, right, 1 minus alpha by 2 and minus 1 plus alpha by 2. He has, one of them is minus 1 minus alpha by 2 and the other one is minus 1 plus alpha by 2. Right, n plus 1 minus alpha by 2 is equal to n plus 1 plus.
Why not you take the above line and make alpha to minus alpha and beta to minus beta?
What?
You take the first line and do beta to minus beta and alpha to minus alpha.
And alpha to minus alpha. That's right. That's what we should get, right? Yeah, that sounds right. Except that, you know, we assumed alpha was positive. But maybe this is the reason that he has had, I'm sorry. Now,
1 minus alpha when you take them, okay.
yeah, maybe yeah, maybe. Let me just do this. Sorry. Right. Yeah, but you're right, because I was as alpha is somewhere between 0 and 1, so 1 minus alpha is always positive. Yeah, so that's okay. Just one minute. Sorry. So that's n plus 1 minus 1 minus 2 plus 1 minus alpha by 2. Okay. So that's n plus 1 minus of 1 plus alpha. Exactly. This is exactly what he has. Okay. So he has n is equal to 1 to infinity and n minus 1 plus alpha by 2. Okay, that's just shifting what was n becomes n plus 1. That may be exactly what you would have got. That may be exactly what you got. Yeah. Okay. And then we want the zero mode part. So let's see. Firstly, we want the power of q. So this thing will multiply q to the power. Now we had alpha squared. No, this was sorry, this was e to the power I alpha by 2. Right, when alpha was 1, it was e to the power IH. So this is alpha squared by 8, which we're going to write as 3 alpha squared by 24. Okay? So this will give us 3 alpha squared minus 1 divided by 24. Okay, so that's good. And then finally, in addition, yeah, that's some very special value. Right? Let's say we're generic at the moment. No, but he has an extra term. Just 1 minute. Yeah. Finally, in addition, we have to take into account that this quantity, this vacuum, doesn't just carry an energy, it also carries a Q charge. Okay? So the Q charge of this is alpha by 2. Okay? And therefore, we have also e to the power I beta, because beta was in this trace, pi e to the power I pi alpha beta by 2. E to the power I pi alpha beta by 2, and now we're in perfect agreement with Wilczynski. Okay. So this is the final formula for Z alpha beta, with alpha defined with boundary conditions with 1 minus alpha, phase 1 minus phase I pi into 1 minus alpha as you go around the circle, and beta being given here. So let's write this once properly. This is for this, where psi of sigma plus 2 pi is equal to e to the power 2 pi I times 1 minus alpha psi of sigma. Okay. All good? Excellent. Okay. So now the next question is, what was this? What was our type 2 partition function in terms of all of these z's? Okay. So the type 2 partition function was what? First, there was trace in the ns plus trace in the, let's say, Raymond plus. Let's say we were interested in this. This was equal to half trace ns into 1 minus, as Indranil pointed out, 1 minus f plus trace in the Raymond into, we could say either plus or minus, that doesn't matter very much, 1 plus minus 1 to the power f, let's say. One of the two sides will have 1 plus, the other will have 1 minus. We'll want both of them. Okay. Now, with your help, I will translate this into the z plus minus language, z alpha beta language. The top guy refers to the periodicity on the circle and has been chosen so that alpha equals 0 is ns sect. Because if we put alpha equals 0, we get a minus sign as we go around. Okay. So this guy is half into z, 0, and 1 here is simple trace, so that's 0. Then minus z, 0, 1. right? Plus, now we've got this in Ramond sector. Ramond sector is alpha equals 1. Z1 plus Z1. This is 0 and this is 1, right? So let's check. 0 was nothing, and this was with a minus 1 to the f. Okay. So the first thing I'm going to do is to look at this quantity and look at it naively, and to see naively whether it is modular invariant, the kind of thing we've been doing the last 3-4 lectures. And naively that works out beautifully, because this guy was ns, so minus, and simple trace, so minus, minus ns Hi Naveen. Can I call you in 10 minutes? I'm in the middle of a class actually. No. I'll call you in 10 minutes. Bye. Okay. Minus ns and a 1. So that's a plus, because the minus 1 to the f makes it plus. Plus z yeah, so this is plus, and this is 0, which is minus, plus, plus, plus. Okay, and there is something. Wrong. So
it's like your minus sign on the inside of the trace.
Z01. That's great. And of course, all these are going to be to the power of 4, right? Because there were 4 pairs of fermions. And I've messed up on something. What have I messed up on? Polchinski gets the Z10 with a minus sign. He gets this guy with a minus sign. Let me think about that. He gets.
Wouldn't the first 3 terms have to have
This is plus minus. That depends on.
Wouldn't the first 3 terms have to have the same sign?
Well, there are extra phases. We come to that in a minute. We come to that possibly next class. This is plus minus depending on whether we're doing type left or right. It's this guy. Where I messed up on this side. Just. And that's a serious one, because it's the vacuum of it's the Ramond sector with nothing is coming with a minus. So just how's that up? Space-time spin statistics. Now I know what he's saying. Yeah. Okay. He's right. You know, we're going to put a minus out here. First, I'm just going to do it, and then we'll worry about why that's the case. You know, what I need to do, of course, is to add together the sectors with the signs that will give me modular invariance. That is the rule. Okay? The sign that works is this. I'm going to do it, but I'm going to give you one interpretation for why that's the case. Okay, one interpretation that makes sense in space-time. Okay? The interpretation is simply the following. It is that, you know, suppose we worked out the one loop partition function. What would this compute for us? What would this compute for us in space-time? It would compute one loop graphs. Right? For instance, it would be one loop contribution to the vacuum energy, or one loop contribution to the thermal free energy if we were doing this at finite temperature. Now, in space-time, a fermionic loop contributes with an extra minus sign. So, torus diagram, when we understand it, what it is in space-time, okay, if you have fermions running in the loop, it's a contribution to the Feynman graph with an extra -1. In terms of determinants, it's simply the fact that the fermionic determinant comes upstairs in space-time, whereas the bosonic determinant goes downstairs. Okay, this is some sort of physical interpretation of this minus sign. Okay, let me say again. What we're going to do is combine together partition functions in these various sectors in a way that is going to make the theory modular invariant.
Now, what if I put an overall minus sign outside?
If you put an overall minus sign outside, well, it won't matter. The overall minus sign won't matter because you're going to multiply this with a right moving thing. So if you put overall minus sign in both, that won't matter. Okay? What's important is that, what in the end is going to be important is that every boson in space-time contribute with a plus sign, and every fermion contribute with a minus sign. What we're going to do is multiply this with something similar on the right moving side. Okay? Now, where do the bosons in space-time come from? They come from either the NS-NS sector or the RR sector. Where do the fermions in space-time come from? They come from the NSR sector or the RNS sector. Okay? So what's important is that this guy and the corresponding Ramon sector on the right side come with a minus. This minus is physical because it's, the one is contributing with a minus sign. So it's not a matter of convention or anything, it's physical. Okay? And it basically is going to translate into, in space-time, bosons contributing with the sign they should, and fermions contributing with the sign they should. Okay? Now you see, what we're doing here is summing over sectors, and the relative phase with which we add the contributions is determined just by the principle of modular invariance. We're going to do what it takes to make it modular invariant. This is, maybe just like an interpretational remark right at the end. Yeah. The combinations that's going to turn out to be modular invariant is this with a minus sign. Okay? So what I'm going to do is now take this and put this with the minus sign and put this with a plus minus. Okay, this to the 4, this to the 4. Okay, this with the whole thing. Now what we need to do is to check that this whole combination is in fact modular invariant. That the whole combination is in fact modular invariant. When we combine together the this and the right moving sector. So I'll leave the actual demonstration for tomorrow, but let me make some quick remarks. The first thing about this, is the following.
Under T transformation, the first one gets a minus sign. First and the second and third gets a relative minus sign.
Yeah, so it looks like it's not working under T transformations. Because it looks like, you see, first let's look at what looks like is working. S transformation looks like it's working. Okay? Because under S transformation, this guy goes to itself, this guy goes to itself, these two go to each other, and they both come with a minus sign. And in fact, that is the reason that modular invariance could not have worked without this minus sign. Because this minus sign was forced on us by physics, as Indranil pointed out. Okay? And this minus sign then is just simply S transformation related to this guy. And it's going to turn out, as we will see, that S transformations behave naive. So these naive, just this naive picture correctly predicts the S transformation properties of these partition functions. However, there will be an anomaly in T transformations. Okay? And this anomaly makes naive manipulation of these with this diagram incorrect. Okay. Now, we'll actually work it out tomorrow, next class. But the first thing, I have to tell you just why is there an anomaly in T transformations. Well, it's very simple. You see, under T transformations, what are we doing? We're doing tau goes to tau plus 1. So under T transformations, what you pick up is e to the power I 2 pi L0 minus L0 bar.
Yes.
Okay?
Yes.
So what we pick up is e to the power.
Rotation.
Exactly. And at funny values of alpha, you can see that these states do not have good L0, do not have particularly nice L0 minus L0 bar values. Okay? That's basically the point. Okay? So the anomaly comes from the fact that L0 minus L0 bar is not in general an integer. Okay? So by using this fact, we will in the next class figure out exactly how these Z alpha betas transform under T transformations.
The ground state will have some non-trivial charge under this operator.
Exactly. The ground state has a non-trivial charge under this operator. Exactly. And we will in the next class figure out exactly how this goes, figure out what the correct T transformation properties are of each of those 4 terms, and then show that with using the correct T transformation laws, correcting this naive picture, it goes back to itself up to an overall phase. And then that overall phase will exactly cancel with the corresponding minus overall phase from the right movers. Okay? So that's basically the game. Let me quick, okay, maybe it's worth going into the details only next time. But of course, you know, since here there is no L0 bar, under T transformations, this part just transforms like e to the power I L0. And the fact that L0 is this funny guy, okay, is going to give us all our funniness. And we'll see how that works. Okay, but next class. Sorry, this